Hello, my friend. There are simple questions so deep that they challenge reality and existence itself. For centuries, scientists have tried to answer them, and they continue to do so to this day. What happened before the Big Bang? Why does time move forward and not backward? Why is our universe exactly the way it is? Tonight, we will explore some of the deepest secrets of the cosmos and slowly unravel these mysteries together. So relax, get comfortable, and listen as we gently unfold the universe's most profound questions. Chapter 1. What happened before the Big Bang? Few questions in science are more thrilling than this one, because to ask what happened before the Big Bang is really to ask whether time, space, and the whole stage of reality had a beginning, or whether something even stranger came first. The reason this question is so difficult is that the Big Bang is often misunderstood. It was not an explosion of matter into empty space, the way a bomb explodes in the air. In modern cosmology, the Big Bang refers to an early hot, dense phase in which space itself was expanding. When scientists run the universe backward using general relativity, they reach a point where density and temperature rise without limit, and the theory itself stops giving trustworthy answers. That breakdown is not a final explanation. It is a sign that our present description of nature is incomplete at the earliest moment we can mathematically approach. That leads to the first and most conservative scientific possibility. Perhaps there was no before in any ordinary sense at all. In that picture, the question is like asking what lies north of the North Pole. The wording sounds reasonable, but the framework itself may stop there. If time is part of the universe rather than a stage outside it, then time may have begun with the earliest state the Big Bang model can describe. This idea is often misunderstood as a claim that scientists know there was literally nothing before the universe. They do not know that. The more careful statement is narrower. It says that according to simple classical models, time itself may not extend farther back, so asking what happened earlier may not be meaningful in the usual way. This is still one of the mainstream possibilities, and it remains scientifically alive because it follows naturally from classical general relativity, even though general relativity is incomplete at such extremes. But there is another major possibility, and it is one of the most influential in modern cosmology. The hot Big Bang may not have been the first stage of the story. It may have been preceded by a very early phase of extremely rapid expansion called inflation. In this view, what we usually call the Big Bang is not the absolute beginning, but the hot aftermath of inflation, when the energy driving that expansion was converted into the particles and radiation that later formed the universe we know. Inflation is taken seriously because it helps explain several otherwise puzzling facts, especially why the universe looks so smooth on the largest scales and why it contains the tiny primordial fluctuations that later grew into galaxies and stars. It is not yet proven in every detail, and physicists still debate what field drove it and how it began. But it is one of the leading ideas about what may have come before the familiar hot Big Bang phase. Even inflation, however, does not completely answer the question. If there was an inflationary phase, one can still ask what came before inflation. At this point, cosmology enters more speculative territory, but still scientific territory. One family of ideas suggests that the universe went through a bounce rather than a beginning. In a bounce model, The present expanding cosmos was preceded by an earlier contracting phase. Instead of collapsing into a final singularity, the universe reached an extremely compressed quantum state and then began expanding again. This is appealing because it replaces a hard beginning with a transition. In some versions inspired by loop quantum gravity, the bounce happens because quantum effects make gravity effectively repulsive at extremely tiny scales, preventing an infinite collapse. These models are mathematically serious, but they are not confirmed, and they depend on approaches to quantum gravity that remain incomplete. So bounce cosmology is a genuine scientific hypothesis, but it is not an established fact. A related but more elaborate set of models is the cyclic or ekpyrotic picture. In these scenarios, our expanding universe was preceded by a long period of slow contraction, and the Big Bang is reinterpreted as a transition between contraction and expansion rather than the first moment of existence. In some versions rooted in higher dimensional ideas, the event we call the Big Bang is associated with the interaction of large structures sometimes described as brains. In broader cyclic versions, this kind of history may happen repeatedly, with the universe going through many rounds of contraction and expansion over enormous spans of time. These ideas are attractive because they try to explain the large-scale smoothness of the cosmos without relying entirely on ordinary inflation, and because they replace the beginning with an ongoing cosmic rhythm. But they face technical challenges, especially in producing a stable, non-singular bounce and matching all observations as cleanly as inflation does. They remain active alternatives, not part of the settled standard picture. There are also string-inspired pre-Big Bang ideas in which the universe may have begun in a very different, simpler state, and then evolved toward the hot expanding phase we later reconstruct. In these approaches, the earliest universe is not born from classical nothingness, but from a previous physical regime governed by string theory. Some of these models resemble bounce scenarios, while others describe an early era in which different fields and dimensions behaved differently from how they do now. These proposals are scientifically interesting because they try to connect the origin of the universe to a candidate framework for unifying gravity with quantum theory. But here again, caution is essential. String-based early universe models are rich and imaginative, yet they are still far from observationally settled. They belong to the serious research frontier, not to established cosmological knowledge. Another important group of hypotheses comes from quantum cosmology, where the universe is treated not simply as a classical expanding object, but as a quantum system. In these approaches, the question is no longer only what material state came first, but what the initial quantum state of the whole universe may have been. One famous proposal says the universe may have had no boundary to the past in the ordinary sense. Instead of beginning from a sharp edge in time, the earliest stage may have been more like a smooth, rounded region where the distinction between time and space becomes blurred. Another well-known proposal describes the universe as quantum tunneling into existence from a state that is not ordinary empty space, but rather the absence of a classical universe. These ideas are among the most subtle in modern cosmology. They are not stories about a familiar earlier world full of stars and galaxies. They are attempts to define what an origin even means when space-time itself becomes quantum. There is also a quieter possibility that gets less attention in popular discussions. perhaps the universe did not begin with a violent transition at all, but emerged from a long-lasting earlier state that was almost static. In so-called emergent universe ideas, the cosmos may have existed in a quasi-stable condition for an extremely long time before shifting into expansion. The attraction of this picture is that it tries to avoid both a singular beginning and a sudden bounce. Instead, the universe gradually leaves a long prehistory and enters the expanding phase we later observe. These models are less dominant than inflationary cosmology and less famous than bounce proposals, but they are part of the broader scientific landscape. They matter because they show that cosmologists are not all imagining only one kind of before. Some imagine a sharp beginning, some a bounce, some a long contraction, and some a nearly timeless prehistory. At this stage, it becomes important to separate what is strongly supported from what is not. The hot Big Bang model is strongly supported from shortly after the beginning of expansion onward. The expansion of the universe, the existence of the cosmic microwave background, and the abundances of the lightest elements all fit that picture extremely well. Inflation is widely used because it helps explain why the universe looks the way it does on large scales, though the detailed physics behind it is still being worked out. Bounce, cyclic, ekpyrotic, string-based, no boundary, tunneling, and emergent scenarios are all serious scientific ideas. But none has yet won decisive observational confirmation. So the honest scientific answer is not that we have one clear picture of what came before the Big Bang. The honest answer is that we have several major classes of hypotheses, each trying to solve the same fundamental problem in a different way. There is one more possibility, and in some ways it is the most radical of all. It may be that the universe at its deepest level cannot be described as having one single classical history before the Big Bang. In quantum cosmology, some formulations suggest that the early universe should be understood through a sum over possible histories rather than one simple past. That does not mean that anything at all happened. It means the familiar idea of one timeline stretching backward may itself fail near the origin. What seems from far away like a single history could emerge from a deeper quantum description in which ordinary time is not fundamental in the way we usually imagine it. This is hard to picture because human thought is built around before and after. But one lesson of modern physics is that reality is not required to match everyday intuition. Just as relativity changed our understanding of space and time, a future theory of quantum gravity may change our understanding of cosmic beginnings even more dramatically. So what happened before the Big Bang? The most careful answer is that scientists do not yet know. And the reason they do not know is not a lack of imagination, but the depth of the problem itself. The main possibilities in current scientific research are these. There may have been no meaningful before, because time itself began with the earliest cosmic state. There may have been an inflationary phase before the hot Big Bang. There may have been a bounce from an earlier contracting universe. There may have been a cyclic or ekpyrotic prehistory. There may have been a string-based pre-Big Bang phase. There may have been a quantum origin described by a no-boundary or tunneling proposal. Or the universe may have emerged from a long-lived earlier state, unlike anything in everyday experience. Some of these ideas may eventually merge. Some may fail. A few may survive future evidence. Right now, the mystery remains open, but it is open in a disciplined scientific way. And perhaps that is a gentle thought to end on. The beginning of everything is not something you need to solve tonight. It is enough to know that even the greatest minds in science still stand quietly at that threshold, looking backward as far as evidence allows, and then meeting mystery. Above you, the universe continues its calm expansion, carrying traces of its earliest moments across the dark, while you are free to let the question rest for now and let the mind grow still with it. Chapter 2. Why the universe exists in this form at all. Few questions feel more profound than this one, because once you ask why the universe exists in this form at all, you are no longer asking only how it began, but why reality became a place with stars, atoms, chemistry, structure, and eventually living minds able to wonder about it. That is a different question from what came before the Big Bang. The first asks about origin. This one asks about shape, character, and possibility. Why does the universe have laws that allow stable matter instead of chaos? Why does it contain long-lived stars rather than only brief flashes of radiation? Why does it produce the ingredients for planets, oceans, and life? Modern science does not yet have a final answer, but it does tell us something important. The universe we live in is not just any imaginable universe. It is a very specific kind of universe with a very specific set of properties. The first step toward understanding this mystery is to notice how much had to go right for anything familiar to exist. Matter had to be stable enough not to vanish immediately. The basic forces had to allow particles to join into atoms. Atoms had to be able to combine into more complex forms. Stars had to be able to ignite and survive long enough to make heavier elements. Space had to expand in a way that allowed matter to gather into galaxies rather than either flying apart too quickly or collapsing too violently too early. These are not poetic requirements. They are physical ones. If the basic features of the universe had been very different, the cosmos might still have existed, but it might have been a place with no long-lived structure, no complex chemistry, and no observers. One way science approaches this question is by studying the laws of physics themselves. At the deepest level, we can presently test in the laboratory. The known particles and several of their interactions are described by a framework that works extraordinarily well. It explains a huge range of phenomena with remarkable precision. But even this success leaves the deeper mystery untouched. A good theory can describe what exists without explaining why this particular pattern exists, rather than another one. It can tell us what electrons, quarks, and photons do. It can tell us how matter behaves. But it does not yet tell us why reality chose this exact menu of ingredients and not some different one. It also does not include gravity in the same unified way, which is one reason physicists do not regard it as the final account of nature. Another part of the mystery lies in the values of the fundamental constants. These are the basic measured quantities that appear throughout physics and chemistry. They are not vague philosophical ideas. They are concrete numerical features of the world, measured with extraordinary precision. Science can determine them more and more accurately, but measurement is not the same as explanation. Knowing the value of a constant does not tell us why it has that value, rather than another nearby one. This matters because the behavior of the universe depends sensitively on some of these values. Change certain constants enough, and atoms would not hold together in the same way. Change others, and stars might burn too quickly, too weakly, or not at all in any familiar sense. So when physicists ask why the universe exists in this form, part of what they are really asking is why the rulebook of nature has exactly these settings. This is where the idea of fine-tuning enters the conversation. The phrase can sound dramatic, and it is often misunderstood. In science, it does not automatically mean that the universe was designed for life. It means something narrower and more careful. It means that some outcomes appear sensitive to the values of certain physical parameters or to the conditions of the early universe. If those values were significantly different, the large-scale world might look very different too. That is a real scientific issue, not just a philosophical one, because physics can explore how stars, nuclei, and structure formation depend on the laws and constants we observe. The mystery is not whether life was the goal of the universe. Science does not say that. The mystery is why the universe turned out to be a place where stable complexity is possible at all. A good example is the existence of chemistry beyond the lightest elements. The early universe began mostly with hydrogen, helium, and tiny traces of lithium. That was enough to make the first generation of stars, but not enough for rocky planets, oceans, or biology as we know it. The heavier elements had to be forged later inside stars and then scattered through space when those stars died. Carbon, oxygen, silicon, iron, and the other ingredients of worlds like ours were not present in abundance at the start. They were built slowly through stellar life cycles. This means the universe had to allow stars not only to form, but to live in ways that gradually enriched the cosmos. A universe with the wrong balance of forces or the wrong large-scale conditions might never have created that chemical richness. So the fact that the universe can make chemistry like ours is already part of the mystery of why it exists in this form. The formation of structure matters just as much. If matter had remained perfectly smooth, galaxies would never have formed. If it had been too violently irregular, large-scale stability might have been lost. The universe needed both order and variation, enough overall regularity to be intelligible, enough unevenness for gravity to gather matter into stars and galaxies. This balance is one reason the cosmos feels so unusual. It is lawful without being featureless. It is structured without being rigid. It allows the gradual emergence of complexity from simple beginnings. That may sound almost philosophical, but it is really a statement about cosmological evolution. A universe capable of becoming interesting is not guaranteed simply by existing. It depends on the kind of universe it is. There is also the mystery of matter itself. According to the broad picture of early universe physics, matter and antimatter should have been created in nearly equal amounts in the hot young cosmos. If that equality had remained exact, the two would mostly have annihilated one another, leaving behind a universe full of radiation and very little lasting matter. Yet that is not what we see. The visible universe is overwhelmingly made of matter. Somewhere in the earliest cosmic history, a small imbalance appears to have favored matter over antimatter. That tiny difference changed everything. Without it, there would be no long-lived stars, planets, or bodies. There would be no stuff in the everyday sense from which complex structures could emerge. Science knows this asymmetry exists because the universe is here in a material form, but the full reason for that imbalance is still not known, and current fundamental theory does not explain it well enough on its own. Then there is the problem of vacuum energy, which is one of the deepest in all of theoretical physics. In ordinary language, empty space sounds like nothing. But modern physics does not treat the vacuum as simple nothingness. Even empty space has physical properties. It participates in the behavior of fields and in the large-scale evolution of the universe. Yet when physicists compare theoretical expectations for vacuum energy with what the actual universe seems to allow, they run into one of the sharpest mismatches in science. The observed large-scale behavior of the cosmos suggests that the vacuum is far more gentle than naive theory might expect. This matters because if the vacuum behaved very differently, cosmic expansion and structure formation would be drastically altered. Galaxies might never have formed in the way they did. So even empty space is part of the mystery. The universe exists in this form not only because matter behaves the way it does, but because the background structure of space itself seems unexpectedly suitable for long-term cosmic development. At this point, several broad possibilities open up. One is that a deeper future theory will show that the universe could not have been otherwise. In that case, what now looks contingent would turn out to be necessary. The constants, particle content, and laws would follow from a more fundamental structure in a way that leaves little room for alternatives. Another possibility is that some features truly could have been different, but that our universe represents one realized outcome among several physically possible ones. In that case, the question becomes why this possibility was selected. A third possibility is more modest and observational. Any observers will always find themselves in a universe compatible with observers, because incompatible universes would contain no one to notice them. This does not fully explain the laws, but it may explain why our observations are filtered the way they are. Science has not yet chosen decisively among these deeper interpretations. What makes this chapter different from the previous one is that the problem here is not mainly about the first moment. It is about why reality has such a fruitful architecture. The universe is old, vast, and often hostile, but it is also astonishingly structured. It contains stable particles, mathematical regularities, stars that make heavier elements, and large-scale conditions that allow matter to gather rather than remain forever diffuse. None of that means the universe was built for comfort. Most of space remains deadly to life. But it does mean that the cosmos is governed by rules capable of producing islands of order within an immense darkness. That is already remarkable. A universe filled only with radiation or short-lived chaos would still be a universe. Ours is something more elaborate. It is a universe that can build. And that is why this question remains so powerful. We do not yet know whether the deep explanation lies in hidden necessity, in selection from many possibilities, or in a framework of physics not yet discovered. We do not know why the constants take the values they do, why matter won over antimatter, or why the laws are so well suited to stable complexity. But we do know that the question is real. The universe did not merely appear. It appeared in a form capable of stars, chemistry, memory, and thought. Somewhere between the first particles and the long life cycles of stars, the cosmos became a place where it could begin, in a small and temporary way, to notice itself. There is something quietly moving in that. The same universe that seems cold and immense also carries within it the exact kind of order from which worlds, lives, and questions can arise. We may not yet know why reality took this shape, but we live inside the answer, even while still searching for it. And perhaps that can be a calm thought to rest with tonight. that you are part of a universe whose structure is deep enough to remain mysterious, but gentle enough, in one small corner, to have made space for stars, for life, and for this moment of reflection. Chapter 3. Why the universe is so smooth on the largest scales. This mystery is one of the most beautiful in all of cosmology, because it asks why the universe, when seen across unimaginable distances, looks so calm, so even, and so strangely well balanced. At first, that may not sound mysterious at all. The universe does not feel smooth when we look at it with our eyes. We see planets, stars, galaxies, clusters of galaxies, and huge dark gaps between them. Space looks clumpy and dramatic, but on the very largest scales, when astronomers step back from the details and examine the broad pattern of the cosmos, they find something surprising. The universe looks remarkably similar in every direction, and remarkably similar from one enormous region to another. In cosmology, this is described with two ideas: homogeneity and isotropy. Homogeneity means that the universe is broadly similar from place to place when averaged over great enough distances. Isotropy means that it looks broadly similar in every direction. Those are not guesses or poetic impressions. They are conclusions supported by observations of the early universe and of the large-scale distribution of matter. The strongest evidence for this smoothness comes from the oldest light we can observe, the cosmic microwave background. This light comes from a time when the universe had cooled enough for radiation to travel freely through space. Before that, the early universe was filled with a hot plasma in which light was constantly scattered by charged particles, so it could not move far without being interrupted. Once the cosmos cooled enough for neutral atoms to form, light was finally able to stream across space. That ancient radiation still surrounds us today. When astronomers map it across the sky, they are not looking at stars or galaxies. They are looking at a relic glow from the young universe. And what that glow reveals is astonishing. The temperature is almost the same everywhere. Not exactly the same, but so close to the same that the tiny differences become one of the deepest clues in cosmology. This is where the real puzzle begins. If distant parts of the early universe were never in contact with one another, why should they look so similar at all? Why should regions separated by enormous stretches of space have almost the same temperature and almost the same overall properties? In ordinary life, things that become similar usually do so because they have exchanged energy or information. A room becomes evenly warm because air circulates. A cup of tea cools because heat spreads into its surroundings. But in the simplest picture of an expanding early universe, some distant regions seem to have been too far apart to communicate in time before that ancient light was released. And yet they still look almost perfectly matched. This tension is known as the horizon problem. It does not mean there is something wrong with the observations. It means that the observations are so smooth that they demand an explanation deeper than the simplest early expansion picture provides by itself. To understand why this is so surprising, it helps to imagine the sky as a giant sphere of ancient light around us. When we compare one side of that sphere to another, we are comparing regions that were already enormously separated when the light began its journey. In the simplest non-inflationary picture, they do not seem to have had enough time to influence one another, equalize their temperatures, or settle into nearly identical large-scale states. And yet, that is exactly what we see. The early universe was not just smooth in a vague sense. it was extraordinarily smooth. That does not mean perfectly blank. Tiny variations were present, and those variations turned out to be crucial. But the overwhelming impression is one of deep uniformity. The young cosmos appears to have started in a state of remarkable large-scale balance. And that is not the sort of thing physics wants to accept without asking why. One possible response would be to say that the universe simply began that way for no deeper reason. In principle, that cannot be ruled out. Nature is not obligated to satisfy human demands for explanation. But science usually prefers a mechanism when one can be found, especially if that mechanism can also explain other observed features at the same time. This is why inflation became such an important idea in modern cosmology. Inflation proposes that before the hot Big Bang phase we usually describe, the universe passed through a brief era of extremely rapid expansion. The core idea is surprisingly intuitive. If the part of the universe we now observe once came from a much smaller region, then that smaller region could have been in causal contact long before it was stretched outward. In other words, the distant parts of the sky we now compare may once have been close enough together to share physical conditions. Inflation would then take that once connected patch and expand it enormously, making the present universe look smooth over vast distances because those regions were once neighbors. This is what makes inflation so powerful. It does not merely say that the universe is smooth, it gives a reason why it could become smooth without requiring a miracle of matching initial conditions across disconnected regions. What now looks like impossible coordination becomes the memory of an earlier closeness. Regions that today seem hopelessly far apart may have inherited similar conditions from a time when they were much nearer together. That is the basic resolution of the horizon problem. It turns a mysterious large-scale sameness into the result of an earlier physical process. That alone would make inflation important, but it does even more than that. The universe is not perfectly smooth, and that imperfection matters just as much as the smoothness. Tiny early differences in density were needed so gravity could later amplify them into the structures we see today. If the early universe had been absolutely uniform, matter would have had no preferred places to gather. There would be no galaxies, no stars, and no planets in the familiar sense. Inflation offers a way to explain these tiny irregularities too. In inflationary models, small quantum fluctuations in the very early universe can be stretched to cosmic sizes during rapid expansion. After inflation ends, those faint wrinkles remain imprinted in the distribution of matter and radiation. Over vast stretches of time, gravity slowly magnifies them, turning almost invisible early unevenness into the richly structured universe of galaxies and clusters we now observe. So inflation helps explain both sides of the mystery at once: why the universe is so smooth overall, and why it is not perfectly smooth. That double success is one reason inflation is taken so seriously. But it is important to say clearly what science knows and what it does not know. Inflation is a leading framework, not a finished final story in every detail. Observations strongly support the idea that something like it happened because it accounts so well for the large-scale smoothness of the universe and for the pattern of tiny primordial fluctuations measured in the cosmic microwave background. Yet cosmologists still debate exactly what drove inflation, how it began, how it ended, and how it fits into a deeper theory that unites gravity with quantum physics. So the smoothness problem is not fully solved in the everyday sense. It is better to say that the most successful explanation we have points toward an early burst of dramatic expansion, while many details remain under investigation. There is another subtle point here that matters for understanding the chapter clearly. When cosmologists say the universe is smooth on the largest scales, they do not mean that every region is identical in every detail. They mean that when you average over enormous distances, the overall statistical properties look very similar. That is why the universe can contain a cosmic web of galaxies, clusters, filaments, and voids while still counting as homogeneous and isotropic on large scales. Local complexity and global smoothness are not opposites. In fact, the present large-scale structure grew out of the tiny deviations from smoothness that were present at the beginning. The broad background was even enough to produce a universal pattern, while the small irregularities were enough to produce local variety. This balance between order and unevenness is one of the most elegant features of cosmology. It is also worth noticing how strange our intuition is on this point. In daily life, we often associate beginnings with disorder. We imagine the start of something as turbulent, messy, or random. But the earliest observable universe appears, on the largest scales, to have been extraordinarily coordinated. Not controlled in a human sense, and not designed in a scientific sense, but ordered enough that distant regions still carry nearly the same ancient thermal memory. That is part of what makes the cosmic microwave background such a profound object. It is not visually dramatic like a supernova or a black hole. It is quiet. It is a nearly uniform bath of ancient light. But hidden inside that quietness is one of the deepest clues we have about how the universe began to take shape. There are still open questions around the edges. Some features in the sky have led scientists to investigate whether the universe is perfectly isotropic, or whether there may be subtle anomalies on the very largest scales. These are active areas of research. But the broad picture remains strong. The early universe was incredibly smooth, with tiny fluctuations superimposed on that smoothness. And the best supported explanations point toward a very early period of rapid expansion. That means the calmness of the cosmos is not a trivial background detail. It is one of the central facts any theory of the early universe must explain. The smoothness is not a decorative property. It is foundational, and perhaps that is one reason this chapter can feel strangely comforting as well as scientific. The universe now contains collisions, collapse, noise, loss, and enormous local violence. But beneath all of that complexity lies evidence that the cosmos began, at least on its largest scales, in an extraordinary state of balance. The vastest structures around you grew from a background so even that its faint whisper still reaches us across the sky. There is something calming in that image. It suggests that complexity can emerge from quietness, and that even a universe full of drama carries, deep in its past, a memory of profound stillness. So as the day begins to loosen and your thoughts begin to settle, it may help to remember that the cosmos itself once rested in near uniform light. And from that gentle smoothness came galaxies, stars, worlds, and this small reflective moment in which the universe, through you, has paused long enough to wonder about its own beginning. Chapter 4. What happens inside a black hole? Few places in the universe are more unsettling or more fascinating than the inside of a black hole, because this is where some of the most successful ideas in physics are pushed all the way to their limit. Black holes are no longer just theoretical objects. Astronomers have strong evidence that they exist, and in recent years they have even imaged the glowing matter around some of them. But even though black holes are real, the question of what happens inside one remains partly hidden from us. That is not because scientists have ignored the problem. It is because black holes create a natural barrier between what can be observed from the outside and what may happen deeper in. The strange thing is that physics can describe that barrier very well, yet still struggle with what lies beyond it. The first important thing to understand is that a black hole is not really a hole in the ordinary sense. It is not an empty tunnel in space, and it is not a cosmic drain sucking everything around it inward. A black hole is a region where matter has been compressed so much that gravity becomes overwhelming. Around that region is a boundary called the event horizon. The event horizon is often described as the point of no return, and that description is basically correct. Once something passes inside it, no light or signal can come back out to the wider universe. This does not mean the event horizon is a hard surface like the ground of a planet. It is not a wall. It is a boundary in space-time that marks where escape stops being possible. This is one reason black holes are so hard to imagine correctly. In everyday life, boundaries are usually visible and solid. A door, a cliff, a window, a shoreline. The event horizon is different. If you were far away, you could not see a glowing line marking where it is. What you would see instead is matter outside the black hole being heated as it falls inward, often becoming very bright before it disappears. That is one reason the famous black hole images do not show the black hole itself like a photograph of a solid object. What they show is glowing material around the black hole and the dark shadow produced by the way strong gravity bends light and prevents some of it from reaching us. The black hole itself remains dark because light that crosses the event horizon does not return. A common myth is that black holes pull more strongly than everything else, simply because they are black holes. That is not true. If the sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting at roughly the same distance. Of course, the loss of sunlight would be catastrophic for life, but the orbital motion itself would not suddenly change because gravity depends on mass and distance. What makes black holes dangerous is not magical suction. It is what happens when matter gets too close. At that point, the curvature of space-time becomes so strong that escape is no longer possible once the event horizon is crossed. Now imagine that something falls toward a black hole. From very far away, an outside observer would see something strange. The falling object would appear to slow down as it approached the event horizon. The light coming from it would become more and more redshifted, meaning its wavelength would stretch and its energy would seem to decrease. It would also become dimmer and harder to detect. To the distant observer, it would seem as if the object never quite crosses the horizon in a clean visual way. Its signals would become weaker and more delayed. This is one of the strange predictions of general relativity. But for the object doing the falling, the experience is different. If the black hole is large enough, crossing the event horizon would not necessarily feel dramatic at that exact moment. There is no painted line in space and no guaranteed impact at the boundary itself. The dramatic difference is not in what is locally felt at that instant, but in what futures remain possible afterward. That difference between the outside view and the falling view is one of the deepest lessons of black hole physics. Outside observers, embers are not disagreeing because one is wrong. They are describing the same reality from different physical situations. To the person falling in, time continues normally for a while. To the distant observer, the black hole seems to hold the object near the horizon longer and longer. This is not a contradiction. It is a consequence of how time and light behave in extremely strong gravity. Black holes force us to give up the simple idea that everyone must describe time and motion in exactly the same way. Sooner or later, another effect becomes important. Gravity near a black hole is not just strong. It also changes rapidly with distance. The side of an object closer to the black hole is pulled more strongly than the side farther away. These differences are called tidal forces. If they become intense enough, the object is stretched lengthwise and compressed sideways. This process is sometimes called spaghettification. The name sounds playful, but the effect is real. In astrophysics, tidal forces near black holes can tear apart stars that wander too close. The details depend on the size of the black hole. Near a smaller black hole, tidal forces can become lethal before or near the event horizon. Near a supermassive black hole, the event horizon may be crossed before those forces become extreme, because the horizon is much larger and the gravitational gradient there can be gentler. So the popular idea that crossing the horizon always means instant destruction is not quite right. The truth depends strongly on the mass of the black hole. Once inside the event horizon, the mystery becomes deeper. In the simplest classical picture, the interior of a non-rotating black hole leads inevitably toward a singularity. A singularity is not best imagined as a tiny physical marble sitting at the center. It is better understood as a sign that the equations of classical general relativity are being pushed beyond where they can give a sensible physical description. In that mathematical picture, density and curvature become unbounded, and the known laws of physics stop functioning in the way we expect. This is crucial. Scientists do not treat singularities as ordinary objects that have been fully understood. They treat them as warnings that the theory has reached its limit. So when people say that everything inside a black hole ends at a singularity, that is true within the classical equations, but it is probably not the final physical story. This is one reason black holes are so important in modern physics. General relativity describes gravity extremely well on large scales. Quantum physics describes matter and radiation extremely well on small scales. But inside black holes, especially near the deepest interior, both kinds of physics should matter at once. That means black holes expose a gap in our understanding. We do not yet have a completed and experimentally confirmed theory that unites gravity with quantum physics in these extreme conditions. So when we ask what happens inside a black hole, the most honest answer is not that science has a full map and is hiding it. The honest answer is that the best current theories point toward an extreme interior, but the deepest part of that interior lies beyond the reach of a complete agreed description. Real black holes may also be more complicated than the simplest textbook case. Many black holes spin, and rotation changes the geometry around them. A rotating black hole is not just the same object with added motion. In theory, rotation gives the black hole a richer structure. The mathematics suggests features like an inner horizon and a different kind of singular behavior than in the simplest non-rotating case. These ideas have inspired countless science fiction stories about tunnels, passages, and hidden exits. But physicists are very cautious here. The exact elegant structures found in ideal mathematical solutions may not survive in the same way once realistic disturbances in falling matter and quantum effects are taken seriously. So it is fair to say that rotating black holes probably have more complicated interiors, but not fair to claim that we know those interiors in detail. Then there is Hawking radiation, which changed the whole subject. In the classical picture, black holes only absorb, but quantum theory suggests that black holes are not completely black. They can emit a very faint form of radiation and therefore lose energy over time. For large astrophysical black holes, this effect is far too weak to matter on human timescales, and far too weak to be directly observed with present technology. Even so, the idea is revolutionary. If black holes can slowly radiate away their mass, then they are not eternal in the simple classical sense. Given enough time, they can evaporate. That means the question of what happens inside a black hole is connected not only to gravity, but also to the long-term fate of the black hole itself. And this leads directly to one of the biggest unsolved problems in theoretical physics: the information paradox. In quantum theory, information about a physical system is not supposed to be destroyed in a fundamental way. But if matter falls into a black hole, and the black hole later evaporates through apparently thermal radiation, what happens to the information about what fell in? Is it somehow encoded in the outgoing radiation? Is it stored in a subtle way near the horizon? Does our understanding of quantum theory or space-time need revision? Physicists have made important progress on this problem, and several promising ideas exist, but there is still no single universally accepted final answer. This means black holes are not merely extreme astronomical objects. They are also places where our deepest theories challenge one another. So what happens inside a black hole? The best answer has layers. According to general relativity, crossing the event horizon means entering a region from which no return is possible, and in the simplest classical picture, the future leads toward a singularity. According to astrophysics, tidal forces can stretch and destroy matter, with the details depending on the size of the black hole. According to quantum theory, black holes may slowly radiate and raise deep questions about information. And according to honest modern science, the deepest interior is not fully understood, because that is exactly where our present theories become incomplete. Black holes are therefore not only dark objects in space, they are one of the clearest signs that human knowledge has reached a boundary and is trying to push beyond it. There is something quietly humbling in that. The universe allows us to detect black holes, orbit them with equations, image their surroundings, and even hear the ripples produced when they collide. Yet it still withholds the final truth of what their interiors become. Perhaps that is why they feel so powerful in the imagination. They are not only symbols of destruction, they are reminders that reality contains regions where certainty grows thin and mystery becomes part of the landscape. And for tonight, that thought does not need to feel frightening. It can feel calm instead, like the dark sky itself, vast, silent, and deep enough to hold unanswered questions without demanding that you solve them before you rest. Chapter 5. Why Time Only Moves Forward. Of all the mysteries in physics, this one may feel the most personal. because the forward movement of time shapes every memory, every change, every loss, and every hope. And yet the deepest laws of nature do not always seem to care very much about the difference between past and future. In daily life, time feels obvious. A glass falls and shatters, but the pieces do not leap back together. Hot tea cools on a table, but it does not pull warmth from the room and become hotter by itself. Smoke spreads through the air, but it does not gather itself back into a neat little cloud. We remember yesterday, not tomorrow. We grow older in one direction. Everything in ordinary human experience suggests that time has an arrow, a built-in one-way flow. But when physicists look more deeply, the mystery becomes stranger. Because the basic laws beneath many physical processes often work almost as well forward as backward. This is one of the most important distinctions in the whole subject. There is a difference between the laws of physics and the large-scale behavior of the world built from those laws. If you watch two billiard balls collide, the motion looks physically reasonable whether the film is played forward or backward. At the microscopic level, many interactions do not contain an obvious marker that says, this direction is the future. That means the one-way character of time does not simply come from a universal command written directly into every process. Instead, physicists are led toward a more subtle idea. The arrow of time that we experience may emerge from the behavior of very large systems, from probability, and from the history of the universe itself. The central concept here is entropy. Entropy is often described loosely as disorder, but it is better understood as a measure of how many microscopic arrangements are possible while still producing the same larger visible state. That sounds abstract at first, but the basic idea is simple. Imagine a room with all the air molecules crowded into one corner. That arrangement is possible in principle, but it is extremely special. There are vastly more ways for the molecules to be spread throughout the room than for them to stay in one corner. So if the gas is left alone, it naturally moves toward the more probable spread out state. Not because a hidden force loves messiness, but because there are overwhelmingly more ways to be spread out than to be neatly concentrated. In this sense, entropy is connected to probability. High entropy states are more statistically common than low entropy states for systems made of huge numbers of particles. This helps explain why so many everyday processes seem irreversible. A broken glass could, in principle, reassemble itself if every molecule moved in exactly the right way. Physics does not forbid that, in the most absolute mathematical sense. But the number of microscopic arrangements corresponding to a shattered glass is so vastly greater than the number corresponding to an intact one that the reverse process is so improbable that, for practical purposes, it never happens. The same logic applies to cream mixing into coffee, perfume spreading through a room, or heat flowing from a warmer object to a cooler one. The second law of thermodynamics expresses this general tendency. In an isolated system, entropy tends to increase. That law is one of the clearest scientific expressions of time's arrow. It is why the world develops in one familiar direction rather than the other. But this answer immediately opens a deeper question. If entropy tends to increase toward what we call the future, why was it lower in what we call the past? Why did the universe begin in a condition from which entropy could rise at all? This is where the mystery of time becomes cosmological. The thermodynamic arrow of time depends on the universe having started in a very special state. If the universe had begun in full equilibrium with entropy already as high as possible, then there would be no strong direction for change. There would be no great flow from lower entropy to higher entropy. There would be no rich history of stars forming, planets cooling, chemistry unfolding, and life feeding on energy differences. The world would be very different from the one we know. So the arrow of time that shapes ordinary life may depend, in the deepest sense, on the fact that the early universe was not just hot and dense, but also unusually low in entropy in a crucial broader sense. This can sound confusing at first, because many people instinctively think that a hot early universe should mean high entropy. The important point is that gravity changes the story. A smooth early universe, before matter had clumped into stars, galaxies, and black holes, can still count as low entropy in a gravitational sense. Gravity tends to make matter clump, and those clumped structures, especially black holes, are associated with enormous entropy. So a nearly uniform early universe was not a state of maximum entropy after all. It was, in an important way, a very special starting condition from which entropy could rise dramatically as structure formed. This is one reason the smoothness of the early universe matters so much. It is tied not only to later structure formation, but also to the very existence of time's arrow as we live it. That means the question, why does time move forward, may really be two questions. One is local and everyday. Why do cups cool, eggs scramble, and memories accumulate only one way? The answer there is thermodynamics and statistical behavior. The other is deeper. Why was the universe ever in a state where such an arrow could exist? That question reaches back to cosmology and to the special nature of the early universe. Science has made real progress on the first question. The second remains one of the deepest open problems in physics. We understand many consequences of the arrow of time far better than we understand its ultimate origin. Memory is a beautiful example of this. We remember the past, not the future, because memory is itself a physical process. A brain forms records by changing its internal state. Those changes are not magically outside physics. They involve energy flow, biological work, and irreversible processes. The same is true of photographs, fossils, tree rings, and digital files. A record is something physical left behind by an earlier state of the world. Records point toward what we call the past because entropy is increasing in the direction in which such records are created and preserved. We do not have memories of the future for the same reason a broken glass does not reassemble itself in ordinary life. The physical world makes records in one thermodynamic direction, not the other. The asymmetry of memory is therefore not separate from the asymmetry of thermodynamics. It is part of the same broad pattern. Relativity adds another layer to this story, but it is a different layer. Einstein showed that time is not absolute in the old sense. Clocks moving relative to one another can disagree about elapsed time. Clocks in stronger gravitational fields can also run more slowly than clocks in weaker ones. This is not speculation. It is part of modern physics and even matters for technologies such as satellite navigation. But relativity does not by itself explain why time has a direction in daily life. It explains how time is measured, how it depends on motion and gravity, and how different observers can experience different rates of time. It does not explain why tea cools rather than heats itself, or why memories point one way. So, it is important not to confuse the flexibility of time in relativity with the arrow of time in thermodynamics. One concerns the geometry and pacing of time. The other concerns the irreversible behavior of large systems. This distinction becomes especially important because popular language often mixes them together. People hear that time slows down in gravity and imagine this must explain why time moves forward. It does not. Gravitational time dilation tells us that clocks at different heights or in different gravitational environments may tick at different rates. Time may pass more slowly for one observer than for another. But both observers still experience their own future as lying ahead rather than behind. Relativity bends and stretches time, but it does not by itself give time its one-way direction. The arrow still comes from entropy and from the low entropy condition of the past. There are still subtleties. In particle physics, there are tiny effects that do distinguish between forward and backward behavior in certain processes. These are real and scientifically important. But most physicists do not think they are the main explanation for the vast everyday arrow of time that shapes shattered glasses, fading warmth, and human memory. Those ordinary asymmetries are overwhelmingly understood through thermodynamics and initial conditions. In other words, the reason your room becomes messy, your coffee cools, and your life unfolds from memory into uncertainty is not mainly because of exotic rare particle effects. It is because you live inside a universe that began in a very special condition and has been moving statistically and thermodynamically away from it ever since. This gives the whole subject a quiet emotional depth. The arrow of time is not only a fact about laboratories and equations. It is the reason moments do not return in exactly the same form. It is the reason stars burn through their fuel, seasons pass, bodies age, and histories accumulate. The very possibility of story depends on it. A universe with no arrow of time would not feel like a world unfolding. It would not contain the same distinction between before and after that gives meaning to memory, change, and cause. So even though the arrow of time can be described with thermodynamics, it is not a cold idea. It is woven into the texture of lived reality. And yet, for all this progress, the deepest question remains open. Why was the early universe in such a low entropy state? Why did the cosmos begin in a way that allowed time to acquire a direction at all? Science can describe the consequences with extraordinary power, but the final reason is still being explored. It may depend on deeper cosmology, on gravity, or on principles not yet fully understood. That means time's arrow is one of those rare mysteries that lives at the meeting point of the everyday and the cosmic. It explains your cooling tea and also reaches back toward the earliest structure of the universe itself. There is something strangely comforting in that. The passing of time can feel sharp in human life, but it is also part of a vast physical order, one that links memory, change, and cosmic history into a single unfolding pattern. You do not need to solve that mystery tonight. It is enough to feel for a moment that the same universe which carries every day away also gave rise to the quiet laws that make change possible at all. And as the night deepens, perhaps that thought can soften the mind a little, that time moves forward not as an enemy, but as part of the long, gentle unfolding of a universe still carrying its earliest secrets into the dark. Chapter 6. Are we alone in the universe? Few questions in science feel more powerful than this one, because it does not ask only how the universe works, but whether life and awareness have appeared anywhere else within it. For most of human history, this question belonged almost entirely to imagination. The stars were distant lights, the planets beyond our own system were unknown, and the chemistry of life outside Earth was a mystery with no real data behind it. Today, that has changed. Modern astronomy has shown that planets are not rare accidents. They are common. Many stars have planetary systems, and some of those planets orbit in regions where liquid water could exist under the right conditions. That does not mean those worlds are alive. But it does mean that the old question is no longer just philosophical. It has become scientific. The most important fact to begin with is also the simplest. Right now, Earth is the only world known to host life. That single fact shapes everything. It means that when scientists talk about life in the universe, they are working from a sample size of 1. We know that life can arise here. We do not yet know how often it arises elsewhere, how easily it begins, or how far it can adapt beyond the conditions found on Earth. This is both frustrating and exciting. It is frustrating because one example makes general conclusions difficult, but it is exciting because even one confirmed second example, even the simplest kind of life on another world, would completely change biology, astronomy, and humanity's understanding of its place in the cosmos. One of the biggest reasons this question became more serious in recent decades is the discovery of planets around other stars. For a long time, people could reasonably wonder whether our own planetary system was unusual. Now we know that planets are a normal result of star formation. Some are giant worlds larger than Jupiter. Some are small and likely rocky. Some orbit close to their stars and are scorched by heat. Some are farther away and deeply cold. Some may have thick atmospheres, oceans, or frozen surfaces. The universe is not just full of stars, it is full of worlds. That alone changes the emotional weight of the question. We are no longer asking whether there might be places for life to exist. We know there are countless places where conditions differ, and among those differences, some may be friendly to life. This is where the idea of a habitable zone becomes important. The habitable zone around a star is the region where temperatures might allow liquid water to exist on the surface of a planet, assuming that planet also has a suitable atmosphere. This idea is useful because liquid water matters deeply in the biology we know. On Earth, water is not just a background feature. It is part of the chemistry of life itself. But the habitable zone should not be treated as a magic answer. A planet in the habitable zone is not automatically Earth-like, and it is certainly not automatically inhabited. It might have no atmosphere at all. It might have a poisonous atmosphere, a runaway greenhouse climate, violet radiation from its star, or a barren rocky surface. The habitable zone is a starting point, not a verdict. That is why scientists now think in a broader way about habitability. Life does not depend on distance from a star alone. It depends on many things working together. The size of the planet matters because it affects gravity and atmosphere retention. The composition of the atmosphere matters because it shapes temperature and chemistry. The geology matters because a world with internal activity may recycle important materials. The magnetic environment matters because strong stellar radiation can strip atmospheres or damage surface conditions. The host star matters because some stars are calmer while others are violent and unstable. A world can look promising in one way and hostile in another. So the search for life is not just a search for the right orbital position. It is a search for whole systems that can remain favorable over long spans of time. There is also an important difference between simple life and intelligent life. This distinction is often blurred in casual conversation, but scientifically it matters a great deal. On Earth, life began very early in planetary history, at least compared with the much later appearance of complex multicellular organisms and, much later still, technological intelligence. That suggests the possibility that simple life may be much more common than intelligent life. A universe with countless microbial worlds and very few civilizations would look very different from a universe crowded with technologically advanced societies. So when we ask whether we are alone, we need to be careful. Do we mean alone as living chemistry? Alone as complex biology? Alone as conscious technological beings? These are related questions, but they are not the same question. That is part of why the Drake equation became so influential. It is often treated as though it were a machine for producing an answer, but that is not really its greatest value. Its importance is that it breaks a huge mystery into smaller scientific uncertainties. How often do stars form? How many stars have planets? How many planets might have conditions suitable for life? How often does life begin? How often does intelligence arise? How often does technology appear that could be noticed from a distance? How long does such a detectable phase last? Some of these questions are now better constrained than they once were. We know much more about planets than earlier generations did, but the biological questions remain deeply uncertain. We still do not know how often life begins, even when conditions seem favorable, or how often evolution leads to intelligence. This uncertainty leads naturally to the famous Fermi paradox. The tension is simple enough to state in everyday language. If the galaxy is old, stars are abundant, planets are common, and intelligent civilizations are not extremely rare, then why do we not see clearer evidence of them? Why is the sky so quiet? Why has no signal been confirmed? Why is there no unambiguous sign of technological life beyond Earth? The silence is not necessarily paradoxical in a strict logical sense, but it is a real scientific puzzle. There are many possible explanations. Perhaps life itself is rare. Perhaps simple life is common, but intelligence is uncommon. Perhaps intelligent life appears, but usually does not last long in a detectable technological form. Perhaps civilizations are not broadcasting in ways we expect. Perhaps we have barely begun to search properly. Or perhaps the distances are so vast and the windows of detectability so brief that overlapping signals are much rarer than intuition suggests. The search itself takes more than one form. One path is the search for biosignatures, which are signs that life may be affecting a planet in ways that can be detected from far away. Often this means looking at atmospheres. Some gases can be interesting because on Earth they are strongly tied to biology. Oxygen is an example. Methane is another. But this part of the science requires great caution. A gas that looks suggestive on one world may have a non-biological explanation on another. Planetary atmospheres are complicated. Chemistry, volcanoes, sunlight, oceans, and geology can all produce signals that might look biological at first glance. So scientists do not look for one magical gas that proves life. They look for combinations of features, and they study the whole planetary context to judge whether life is the best explanation. This caution is one of the most important parts of the entire subject. The discovery of life beyond Earth will probably not come as a single dramatic cinematic moment in which one telescope sees one perfect clue and everything becomes certain at once. it is more likely to come through layered evidence. Scientists may find a promising atmosphere. Then they may test whether non-living chemistry could explain it. They may study the star, the climate, the energy sources, and the likely surface conditions. They may compare many possible models. Over time, the case may become stronger and stronger until the biological explanation becomes the most convincing. That is how serious science usually works. Not by one overwhelming flash, but by patient exclusion of alternatives. Another path is the search for technosignatures. These are signs not just of life, but of technology. Radio signals are the best known example, but they are not the only possibility. In principle, advanced technology might leave other traces, such as unusual light patterns, industrial atmospheric chemicals, or large structures that affect starlight in detectable ways. But here again, caution is crucial. Extraordinary claims require extraordinary evidence, especially in a field where false alarms are easy and the implications are enormous. So far, no confirmed technosignature has been found. That does not mean intelligence is absent elsewhere. It means only that the search has not yet produced proof. The solar system still matters too. When people think about life beyond Earth, they often jump immediately to distant exoplanets. But nearby worlds remain extremely important because they can be studied in much greater detail. Some icy moons in the outer solar system appear to contain oceans beneath their frozen surfaces. These environments are especially interesting because they may hold liquid water, chemistry, and energy sources even far from the warmth of the sun. That broadens the search. Life may not require an Earth-like surface under an Earth-like sky. It may be able to survive in hidden oceans, underground environments, or other niches that are very different from the conditions that dominate human imagination. So the search for life is not just a search for another Earth. It is a search for the possible range of living environments in the universe. There is also a deeper uncertainty beneath all of this. Scientists do not yet possess a perfect definition of life that settles every edge case. We know life when we see familiar examples of it on Earth, but when imagining unfamiliar chemistry elsewhere, boundaries become less obvious. Must life use water? Must it be carbon-based? Must it reproduce in ways like Earth organisms? Must it evolve by Darwinian selection? These are not signs of weakness in the field. They are signs that the field is dealing honestly with a very profound question. Before we can fully recognize alien life, we need to understand both what life is and how broad the category might be. What can we honestly say right now? We can say that the universe contains a huge number of planets. We can say that some of them are rocky, and some orbit in regions where liquid water could exist under the right conditions. We can say that the chemistry of life is not obviously unique to Earth, because the elements needed for life are widespread in the cosmos. We can say that scientists are developing better ways to study planetary atmospheres and search for biosignatures. We can say that no confirmed extraterrestrial life has yet been found. And we can say that this question is no longer trapped in myth. It has become a real scientific frontier. That may be the most remarkable part of all. Humanity is living in the period when one of its oldest questions has started to move from wonder into measurement. We do not yet know the answer. The universe remains quiet, but it is not an empty quiet. It is a working quiet, filled with telescopes, spectra, planetary models, careful doubt, and patient listening. Somewhere among distant atmospheres, buried oceans, or signals too faint for us to catch so far, the answer may already exist. And whatever that answer turns out to be, it will change the meaning of the night sky. If we are alone, then life on Earth is even more precious than we usually allow ourselves to feel. If we are not alone, then the universe has found more than one way to wake up and look back at itself. Either way, the question reaches beyond science into something deeply human. It asks whether life is a local accident or a wider tendency written into the structure of the cosmos. And perhaps that is why this mystery can feel both exciting and calming at once. Tonight, as the stars rest above you in their silence, it is enough to remember that you belong to the small part of the universe that has learned to ask the question seriously. Whether the cosmos is full of living worlds or holds only this one, the fact that matter has become curious enough to wonder is already something extraordinary. Chapter 7. How large the universe really is. This is one of the grandest questions in all of science, because the moment you ask how large the universe really is, you are forced to confront the possibility that reality may be far bigger than anything the human mind was built to imagine. In ordinary life, size feels simple. A table has edges, a room has walls, a mountain has a height, even a planet can be measured across. But the universe is not like a stone sitting in empty space. It does not come with a visible border, and it does not present itself to us as a single object we can step back from and measure all at once. That is why this question is much deeper than it first appears. Before we can ask how large the universe is, we have to ask what part of the universe we are even talking about. The first crucial distinction is between the observable universe and the universe as a whole. The observable universe is the part from which light has had enough time to reach us since cosmic history began. Because light travels at a finite speed, and because the universe itself has a finite age, there is a limit to how far we can see. This does not mean there is a wall out there. It means there is a horizon to our view. Beyond that horizon, there may be more universe, but the light from those regions has not reached us yet. So when scientists say they can estimate the size of the observable universe, they are not claiming to know the size of everything that exists. They are describing the largest region that can currently be studied through incoming signals. That alone would already be astonishing, but the story becomes stranger. Many people hear that the universe is about 13.8 billion years old and assume that the most distant visible edge must therefore be about 13.8 billion light years away. That sounds reasonable, but it leaves out one essential fact. Space has been expanding while the light was traveling. So when the light from the most distant observable regions first began its journey toward us, those regions were much closer than they are now. As the light moved through the cosmos, space itself stretched. That means the sources of that light are now far farther away than a simple light travel time picture would suggest. This is why the observable universe is estimated to be roughly 92 billion light-years across, rather than only twice the age of the universe measured in light-years. This can feel difficult to picture because our intuition is shaped by movement through ordinary space, not by space itself growing. In daily life, we imagine distance as something fixed, like the length of a road. But on cosmic scales, distance is dynamic. Galaxies are not simply rushing through a static emptiness away from one central point. The large-scale picture is that space itself is expanding, carrying galaxies with it. This is one reason the old image of the Big Bang as a firecracker exploding outward from a center is so misleading. In the modern view, the expansion happened everywhere, not from one special location. There is no single central point in the ordinary sense from which everything moves outward. Every observer, wherever they are, sees distant galaxies receding on the largest scales, because the large-scale fabric of space is stretching throughout the universe. That fact leads to one of the most beautiful and difficult ideas in cosmology. The universe does not have a center in the way most people first imagine. This does not mean it has no structure. It means the structure is not like a blast spreading into pre-existing emptiness from one middle point. If the universe is homogeneous on very large scales, then every region can appear locally central to its own observers, without there being any true central location for the whole cosmos. This is deeply counterintuitive, because the human mind is comfortable with circles, explosions, and objects inside larger containers. But the universe is not known to be inside anything larger in that familiar sense. Asking where the center is may be like asking for the center of the whole surface of the Earth in a flat map sense. The question comes from intuition, but the reality is built differently. Once we understand that, another question naturally appears. If the universe has no ordinary center and no visible edge, does it at least have an overall shape? Here science becomes more subtle still. Cosmologists study the large-scale geometry of space itself. On the biggest scales we can measure, the universe appears to be very close to flat. This does not mean flat like a sheet of paper in ordinary visual terms. It means that, on the largest measurable scales, space does not show strong overall curvature. If the universe had strong positive curvature, it would be more like the three-dimensional analog of a sphere. If it had strong negative curvature, it would be more like a saddle in a higher dimensional sense. But current observations suggest that the large-scale geometry is very close to flat. That matters because it changes what kinds of overall universe are still possible. Yet even a universe that looks flat to us does not immediately tell us whether the whole thing is finite or infinite. This is one of the most important points in the entire chapter. Flatness does not settle the question of total size. A flat universe could, in principle, extend forever. But it could also be finite if space is connected in a more subtle way, wrapping around on itself without having an edge. That sounds strange, but it is mathematically possible. In that kind of universe, you could in principle travel far enough in one direction and eventually return to where you started. Not because there is an outer boundary, but because space is connected in a closed way. So when scientists say the universe appears flat, they are not saying it must be infinite. They are saying that the large-scale geometry we can observe does not show obvious curvature. The question of total size remains open. This is where the mystery becomes especially deep. Science can estimate the size of the observable universe with impressive confidence, but it does not yet have a reliable measurement of the total size of the entire universe. That is not because scientists have been careless. It is because the relevant evidence may lie beyond the horizon of what can be observed. If the universe is much larger than the observable part, then the clues that would reveal its full size or overall topology may simply be too far away for us ever to detect directly. In that sense, the problem is not only technical. It may be built into the structure of reality itself. Better telescopes can reveal more galaxies, fainter light, and earlier stages of cosmic history, but they cannot automatically overcome the finite speed of light and the finite age of the observable cosmos. Still, even the observable universe alone is beyond ordinary comprehension. Our home galaxy, the Milky Way, contains at least 100 billion stars. That already feels enormous. Yet the observable universe contains at least 100 billion galaxies, and possibly more, depending on how faint and small a galaxy one includes in the tally. That means the number of stars within the observable universe climbs to scales so large that they stop feeling like countable objects and begin to feel more like a statement about vastness itself. Human beings evolved to think in terms of villages, forests, distances walked in a day, and perhaps seas or mountains. Even one galaxy overwhelms that intuition. The observable universe overwhelms it many times over. But the psychological shock of those numbers can also mislead us if we are not careful. A huge number of galaxies does not by itself tell us whether the whole universe is finite. It tells us only that the observable part is immense. The temptation is to assume that immeasurably large and infinite are basically the same thing. Scientifically, they are not. A thing can be unimaginably large and still finite. A thing can also be infinite in principle, even if we can observe only a limited patch of it. This is why cosmologists are disciplined about language. They do not usually say, as a settled fact, that the universe goes on forever. They say instead that the observable part is measurable, that the whole universe is larger than that, and that the total extent remains unknown. That restraint is part of what makes the science trustworthy. There is another subtle issue here as well. When people ask how large the universe is, they often imagine one simple distance, as though there must be one final cosmic diameter. But in cosmology, distance itself is not always a single straightforward thing. There is the time the light has spent traveling. There is the current separation between us and the source that emitted that light. There are other carefully defined distances that help physicists compare observations in an expanding universe. This does not mean the subject is arbitrary. It means that cosmic distance is more layered than the distance from one town to another. Once space expands, how far away depends partly on what exactly you want to know. Are you asking how long the light traveled, where the source is now, or how much the universe has stretched in the meantime? Those are related but not identical questions. All of this helps explain why the size of the universe is not just a matter of giant numbers. It is a matter of understanding what can be observed, how space expands, what geometry the cosmos has on the largest scales, and whether the whole universe is finite or infinite. The remarkable thing is that science has learned enough to ask these questions precisely without yet being able to close them completely. We know the observable universe is astonishingly large. We know there is no ordinary center. We know space is expanding. We know the large-scale geometry appears very close to flat. But we do not yet know whether the total universe ends, wraps around, or extends forever beyond our cosmic horizon. That is what makes this chapter different from the next mystery. Here the main question is not yet what lies beyond what we can see. It is how to think correctly about the size of the part we can see and why that visible size is not the same as total reality. The observable universe is already so enormous that it can hold at least 100 billion galaxies and more stars than the mind can meaningfully picture. Yet even that may be only a local window onto something far greater. The scale is not merely large. it is humbling in a deeper way, because it reminds us that visibility is not the same thing as totality. And perhaps that is the quiet emotional truth hidden inside the science. The universe is not just bigger than a planet or a galaxy, or even the great sphere of everything we can observe. It may be larger than any complete map we will ever draw. There is something strangely calming in that. It means reality is wider than the limits of any one day, any one life, or any one fear. The cosmos remains immense enough to carry unanswered questions without collapsing under them. And tonight, from one small world inside one galaxy, inside one observable patch of a possibly far greater whole, you are allowed to rest inside that vastness for a moment and let it make your own worries feel a little smaller. Chapter 8: What Lies Beyond the Observable Universe? This is one of the strangest questions in all of cosmology, because the moment you ask what lies beyond the observable universe, you are no longer asking only about distant objects, but about the very limits of what any observer can know. The observable universe is not the whole universe in the everyday sense. It is the region from which light, or any other signal moving at the speed of light, has had enough time to reach us since cosmic history began. That means the edge of the observable universe is not a wall in space, and it is not the place where reality ends. It is a horizon created by the finite age of the universe, the finite speed of light, and the long history of cosmic expansion. Science can describe that horizon with great confidence, but once we ask what lies beyond it, the question becomes both scientific and deeply philosophical. The first thing to understand is that observable does not mean all that exists. It only means all that can have influenced us so far through signals that had time to arrive. If there are galaxies beyond that horizon, they are not outside the universe. They are simply outside our present view. This is a crucial distinction. People often imagine the observable universe as a glowing bubble floating in a larger black emptiness, with some kind of outer shell marking the end of everything we can see. But the real picture is subtler. The horizon is not a physical barrier hanging in space like a giant sphere of glass. It is a limit on causal contact. It marks the distance beyond which information has not yet had time to reach us. So when we ask what lies beyond it, we are not asking what lies beyond the universe. We are asking what lies beyond our current access to it. That difference matters because the most conservative scientific answer is actually very simple. Beyond the observable universe, there is most likely more universe. The large-scale cosmos that we can measure appears remarkably homogeneous and isotropic, meaning that when we average over enormous distances, it looks broadly similar from place to place and in every direction. This does not mean every local region is identical. It means the universe, on the largest scales, follows the same broad pattern everywhere we can test. If our observable region is not special, then the simplest expectation is that the same broad cosmic fabric continues beyond the horizon. There may be more galaxies, more clusters, more voids, more cosmic history, and more regions following the same general laws of physics. We cannot directly observe them at present, but the standard cosmological picture suggests that the universe does not suddenly stop just because our view does. Still, it is important not to oversimplify that statement. Saying more universe does not mean a perfect copy of our neighborhood repeated like wallpaper. It means more space-time governed, as far as evidence suggests, by the same large-scale rules. The details may differ. There may be different galaxies, different stars, different local histories of planet formation, and different arrangements of matter. What current cosmology supports is not sameness in every detail, but continuity in the broad statistical sense. The region beyond our horizon is therefore not expected to be a strange exterior realm detached from the rest of reality. Under the standard picture, it is best understood as the continuation of the same universe, extending beyond the distance from which signals have reached us so far. The reason this question becomes so deep is that the observable horizon is shaped by expansion. Light does not simply cross a static stage toward us, while everything else stays fixed. As the universe expands, the space between distant regions changes while the light is traveling. That means the horizon is not just about age and speed. It is also about the growth of the cosmos itself. In the previous chapter, the focus was on how large the observable universe is, and why that visible size is much larger than simple light travel intuition suggests. Here, the important point is different. The horizon is not merely a large distance. It is a moving limit created by the history of space-time. That is why what lies beyond it cannot be treated like an ordinary unknown land beyond a mountain range. It belongs to a universe whose geometry and expansion shape what can ever be seen. This is where inflation becomes important again, but in a new way. Inflation is the idea that the very early universe went through a brief period of extremely rapid expansion. One of its consequences is that the region we now observe may be only a tiny patch of a much larger whole. In other words, the observable universe may be a local window into a far vaster expanse, created when a once small region was stretched enormously. This helps explain the smoothness and flatness of the observable universe, but it also changes how we think about what lies beyond our horizon. If inflation occurred, then the universe beyond what we can see may not just be a little bigger. It may be vastly, perhaps unimaginably larger than the visible region. Our entire observable universe could be only a small, smooth patch within a far greater cosmic structure. At this point, a more speculative possibility enters the picture. Some inflationary models suggest not merely one enormous universe larger than our horizon, but a kind of eternal inflation in which different regions stop inflating at different times. In such pictures, one can imagine many cosmic domains, sometimes called bubble universes, forming within a larger inflating background. Some versions of this idea even allow the possibility that different domains could realize different physical conditions. This is one path by which multiverse ideas enter modern cosmology. But caution matters here more than anywhere else in the chapter. Inflation itself is a major part of mainstream cosmology. The multiverse consequences of some inflationary models are much more speculative. They are discussed seriously in theoretical physics, but they are not directly observed, and they are not established facts on the same level as cosmic expansion or the cosmic microwave background. So when we ask what lies beyond the observable universe, it is scientifically responsible to distinguish between what is strongly suggested and what remains highly conjectural. There is another subtle point that makes the subject even stranger. One might think that, given enough time, the observable universe will simply keep growing and eventually reveal more and more of what lies beyond. In one sense, that is true. As time passes, light from some more distant regions can continue to reach us. But the story is not unlimited. Because the expansion of the universe is accelerating, There are regions so distant that light emitted from them now will never reach us in the future. This introduces a second kind of horizon, often called the cosmic event horizon. The observable universe concerns what has been able to affect us so far. The event horizon concerns what can ever affect us, even in principle, in the future. This is one of the most profound ideas in modern cosmology, because it means some parts of reality may exist forever outside any possible direct communication with us. They are not hidden because our telescopes are too weak. They are hidden because space-time itself prevents the signals from ever arriving. That changes the emotional meaning of the question. Some mysteries are temporary. A better instrument, a longer observation, or a more sensitive detector can solve them. But the universe also seems to contain limits that are not merely technical. There may be regions that are part of the same cosmos and yet are forever beyond direct observation. Science is still powerful in the presence of such limits because theories about unseen regions can be constrained by what we do observe. The flatness of the observable universe, the pattern of the cosmic microwave background, and the large-scale distribution of matter all give us clues about what the larger universe might be like. But clues are not the same as direct inspection. Beyond a certain point, cosmology becomes the science of carefully extending what is supported while remaining honest about what cannot presently be tested. This is why the question does not have a single dramatic answer. It has layers. On the most conservative level, beyond the observable universe, there is probably more universe. On a more ambitious but still serious level, inflation suggests that the total cosmos may be vastly larger than the part we can see. On a still more speculative level, some theories allow a multiverse of many domains. And on the deepest level, there may be aspects of the total cosmic structure that no observer inside our region can ever verify directly. The universe may be finite or infinite. It may wrap around in a topology too large for us to detect. It may continue smoothly beyond our horizon in all directions, or it may be stranger still. The point is not that anything is possible. The point is that several possibilities remain open, and science ranks them by how well they are supported rather than by how exciting they sound. There is something deeply moving in that restraint. It would be easy to fill the unseen with fantasy, to treat the horizon as a stage curtain hiding whatever the imagination most wants to project. But the scientific approach is quieter and, in its own way, more beautiful. It says that the visible universe already reveals enough order to make careful inferences possible, yet not enough to let us confuse inference with certainty. It teaches patience in the face of scale. It reminds us that the unknown is not always a blank void waiting for stories. Sometimes it is a continuation of the same reality, still governed by law, but simply unreachable from where we stand. And perhaps that is the calm thought hidden inside this mystery. Beyond the furthest light that has ever reached us, reality may continue in silence, not as a magical elsewhere, but as more of the same great universe whose edges we can never fully hold in mind. That does not make our small visible patch unimportant. It makes it precious. Everything ever seen, measured, imaged, and wondered about belongs to this brief illuminated region from which the cosmos has managed to speak to us. Beyond it, there may be more galaxies, more darkness, more history, and more futures forever outside our reach. But here, within one tiny part of the whole, the universe has already become self-aware enough to ask what lies farther still. Chapter 9. Why gravity is so strange. Gravity is the most familiar force in human life, and yet the deeper science looks into it, the stranger it becomes. Because the same thing that makes a dropped object fall to the floor also bends light, slows time, shapes galaxies, creates black holes, and still resists our best attempts to fit it neatly into the rest of physics. We feel gravity every moment, so it seems ordinary. It gives weight to the body, keeps oceans on Earth, holds the moon in orbit, and keeps Earth moving around the sun. For a long time, that familiarity made gravity seem simple. It looked like an invisible pull between masses, something reliable and direct. That picture was powerful, and in many situations it still works beautifully. But modern physics revealed that gravity is not just a force in the old everyday sense. It is something deeper and more surprising. The first great shock came with the realization that gravity is tied to geometry. In the modern view, gravity is not best understood as one object pulling another across empty space by an invisible string. Instead, mass and energy change the shape of space-time itself, and objects move through that curved space-time in the most natural paths available to them. This is one of the hardest ideas to absorb because it asks us to stop thinking of space and time as a fixed stage. In ordinary intuition, space is just where things are, and time is just what clocks measure. But gravity shows that the stage is not passive. The stage bends. Time does not flow identically everywhere. Paths that look straight in one sense can become curved because space-time itself is curved. A useful way to feel this idea is to think about falling. In everyday language, we say that gravity pulls us downward. But in the modern description, a freely falling object is not being yanked through space by a rope-like force. It is following the straightest path possible in curved space-time. The reason that path leads toward Earth is that Earth's mass changes the geometry around it. This sounds abstract, but it has observable consequences. Light passing near a massive object bends. Clocks in stronger gravity run more slowly than clocks farther away. The path of a planet around a star is not just the result of a tug. It is the result of moving through curved space-time. Gravity is strange because it does not merely move things around within the universe. It changes the structure of the universe in which motion happens. That alone would be remarkable enough. But gravity becomes even stranger because it acts on everything. Electromagnetism acts on electric charge. Some forces matter only on tiny subatomic scales. Gravity is different. Anything with mass or energy participates in it. Even light, which has no rest mass, does not escape gravity's influence. Light follows the shape of space-time too, which is why massive objects can act like lenses and bend the path of distant starlight. This universality makes gravity feel almost democratic. Nothing gets special permission to ignore it. Matter feels gravity. Radiation feels gravity. Time itself feels gravity. That is one reason it is so hard to escape the sense that gravity is not just another item on a list of forces. It feels more like a built-in feature of reality itself. And yet, despite this universality, gravity is also astonishingly weak. This is one of the strangest facts in all of physics. On very small scales, gravity is far weaker than the other known interactions. A tiny magnet can lift a metal object against the pull of the entire Earth. That is an extraordinary thing when you stop and think about it. An everyday handheld magnet can overcome the gravitational pull of a planet because electromagnetic effects are so much stronger at small scales. So how can gravity be both the weakest known interaction and the one that dominates the structure of the cosmos? The answer lies in patience and accumulation. Gravity is always attractive in the ordinary situations we encounter, and it acts across unlimited distance. Electrical effects often cancel because positive and negative charges balance out. Gravity does not cancel in the same simple way. Mass gathers mass. A little attraction adds to more attraction, and over enormous distances and immense spans of time, that steady pull becomes overwhelming. Gravity may be weak in the laboratory, but it is sovereign in the sky. It organizes gas into stars, binds stars into galaxies, helps shape planetary systems, and governs the motion of matter on the largest scales we can observe. So gravity is strange because it is weak where life is close and immediate, but powerful where the universe has room and time to let it build. This slow, patient power gives gravity a very different character from the more violent image many people carry in their minds. Gravity is not only the force of collapse, it is also the force of structure. Without it, stars would never form. Galaxies would not gather into the patterns we see. Planets would not orbit suns. There would be no long-lived cosmic architecture. In that sense, gravity is one of the great sculptors of the visible universe. It creates order not by sudden action, but by endless quiet influence. Gas clouds drift, matter gathers, compression rises, stars ignite, heavier elements are forged, and worlds eventually emerge. The universe we look at is, to a remarkable extent, gravity's work made visible. But gravity does not only shape motion and structure, it also changes the pace of time. This is one of its most unsettling features. In stronger gravitational fields, time passes more slowly than in weaker ones. This is not poetry and not science fiction. It is part of the physical world. A clock closer to a massive object will tick more slowly than a clock farther away, all else being equal. Even on Earth, this effect is measurable. The difference is tiny in everyday life, but it is real, and modern technology must account for it. This means gravity does not just bend paths through space, it reaches into duration itself. It changes how quickly time unfolds depending on where you are. That is a very strange property for something so familiar. The weight you feel in your own body is tied, in a deep sense, to the way reality measures time. The more one thinks about that, the stranger it becomes. Human intuition treats time as a universal river flowing equally everywhere. But gravity breaks that simplicity. There is no single perfect cosmic clock ticking the same way for all observers in all places. Time becomes local, shaped by motion and by gravity. Yet this is not the same question as the arrow of time explored earlier. Gravity does not explain why time feels one way in ordinary experience. What it does is reveal that the rate of time is not fixed. Gravity reshapes the pace of reality itself. So even before we reach the deepest mysteries, gravity has already forced us to give up the old comforting image of a simple universe with one universal clock. Then, there are gravitational waves, which show another side of gravity's strangeness. If gravity were only a static pull, there would be no reason for moving masses to send disturbances outward through space-time. But when massive objects accelerate, especially in extreme systems like merging black holes or neutron stars, they can create ripples in space-time itself. These ripples travel across the universe, carrying information about the events that made them. This is one of the most extraordinary discoveries in modern astronomy, because it means space-time is not a silent background. It can tremble, It can carry a record of violent cosmic events across vast distances. In a sense, gravity can make the universe ring. This matters not only because it confirms deep theory, but because it changes how we observe the cosmos. For most of history, astronomy depended on light. Now gravity has become a messenger too. Colliding black holes can be detected through the ripples they send through space-time, even when they emit little or no light for ordinary telescopes to see. That means gravity is not just the thing that shapes the universe from behind the scenes. It is something we can now listen to in its own language. The universe speaks not only in light, but in distortions of space-time itself. That is an astonishing change in perspective. Gravity becomes stranger still when it acts on itself. In older ways of thinking, forces operate on a fixed background. In the modern description, the gravitational field is part of the geometry of space-time, and that geometry can influence itself in nonlinear ways. This means gravity is not simple to calculate in extreme situations. It can feed back into the very structure through which it operates. This is one reason the mathematics of general relativity is so rich and so difficult. It also explains why extreme regions, such as those near black holes or in the earliest universe, become places where gravity is not just strong, but conceptually difficult. The field does not merely live in space-time. It is space-time. And when space-time becomes extreme, ordinary intuition collapses. And then we come to perhaps the deepest mystery of all. Gravity does not fit comfortably into quantum physics. The rest of modern microscopic physics is described using quantum ideas with extraordinary success. Those ideas explain atoms, particles, radiation, and a huge range of phenomena with precision. Gravity, by contrast, still stands partly apart. We have no completed and experimentally confirmed theory that fully unites gravity with the quantum world. This is one of the great unfinished tasks in physics. On everyday scales, this gap does not matter much. But in extreme places, such as the deepest interior description of black holes or the earliest moments of the universe, both gravity and quantum effects should matter at once. There, our best theories begin to strain against one another. This is why gravity often feels like both a solved and an unsolved problem at the same time. On the one hand, it is one of the most precisely tested parts of physics. Its predictions about light bending, time dilation, orbital motion, and gravitational waves have been confirmed again and again. On the other hand, it still refuses to become fully comfortable inside the broader framework that describes the rest of fundamental physics. We know gravity works. We know many of its rules. We do not yet know how to finish its story. There is something both triumphant and humbling in that. One of the greatest achievements of science remains incomplete at its deepest level. There are several reasons people suspect that something even deeper may be waiting. Why is gravity so much weaker than the other interactions on small scales? Why does space-time have the structure it does? Is gravity truly fundamental, or could it emerge from something more basic, perhaps connected to information, quantum entanglement, or some still unknown layer of reality? These are not idle philosophical questions. They are active scientific possibilities. Some ideas imagine tiny particles carrying gravity, often called gravitons, though none has been detected. Other ideas suggest gravity may not need to be quantized in the same simple way as the other forces. Still others propose that space-time itself may emerge from deeper quantum relationships. None of these possibilities has yet won decisive confirmation. That uncertainty is part of what makes gravity so compelling. It is familiar enough to feel in every step and deep enough to remain partly mysterious even after centuries of study. It is both intimate and cosmic. It keeps your feet on the ground and bends the paths of galaxies. It makes apples fall and black holes merge. It shapes the pace of clocks and the history of the universe. It is the most ordinary thing in human experience and one of the least ordinary things in physics. Perhaps that is why reflecting on gravity can feel strangely calming as well as unsettling. The same hidden order that holds you gently to the earth also holds stars together, guides planets through their paths, and folds space-time across the dark. Gravity is a reminder that the ordinary and the profound are not separate worlds. The quiet weight of your own body belongs to the same mystery that shapes the cosmos. And tonight, that can be a peaceful thought to rest with, that even the simplest sensation of being held in place is part of a reality vast enough to remain mysterious, patient enough to build worlds, and steady enough to carry you through one more night beneath the stars. Chapter 10. Will the greatest cosmic mysteries ever be solved? This may be the deepest question in the whole journey, because it asks not only what the universe is hiding, but whether there are truths so far beyond us that no telescope, detector, or theory will ever fully bring them into view. Science has a long history of turning mysteries into knowledge. There was a time when planets around other stars were only imagined, when black holes were mostly mathematical possibilities, and when gravitational waves were elegant predictions with no direct detection. Today, those things belong to mainstream astronomy. New observatories have already changed what humanity can know, and more are on the way, including future missions aimed at studying exoplanets in far greater detail, mapping the large-scale universe more precisely, and detecting gravitational waves from space as well as from Earth. That history matters because it tells us something important at the start. Some mysteries feel permanent only because the right tool has not existed yet. That is the hopeful side of the story. The more difficult side is that cosmology is not only a science of hard problems, it is also a science of hard limits. In everyday life, when something is hidden, we usually assume we could see it if we walked closer, shined a brighter light, or built a better instrument. But the universe does not always work that way. Some limits are not technical, they are built into space-time itself. The observable universe is limited by the speed of light and by the age and expansion history of the cosmos. That means some regions may always remain beyond direct access, not because human beings are still primitive, but because reality itself does not allow every signal to reach every observer. When science reaches those horizons, the question is no longer only whether we are clever enough. It becomes whether the universe is willing, in principle, to reveal certain things from where we happen to stand. Even with those limits, there are strong reasons to believe that many of today's great mysteries will become much clearer. Astronomy is no longer confined to visible light. The universe is now studied through radio waves, infrared light, X-rays, gamma rays, particles, and gravitational waves. Each new channel has revealed things older methods could not. Future exoplanet observatories are being designed not only to count more planets, but to examine some of their atmospheres in far greater detail and search for possible signs of habitability or even life. Future gravitational wave missions, are expected to detect classes of cosmic events that current ground-based detectors cannot measure well, including systems involving supermassive black holes and other sources that trace the deep history of space-time. What this means in simple terms is that the universe is still speaking in languages we have only recently learned how to hear. When new instruments open a new channel, entire categories of mystery can change from philosophical to measurable. The search for life beyond Earth is one place where that change may be especially dramatic. Right now, science cannot say whether life is common or rare, but it can say that planets are abundant, that many stars host planetary systems, and that future observatories are being built specifically to study potentially habitable worlds more directly than ever before. That does not guarantee that signs of life will be found soon, or even at all, but it does mean the question is moving steadily out of pure speculation. A mystery does not need to be solved all at once to become more scientific. It can become sharper, narrower, and better framed. We may move from asking whether life exists elsewhere to asking which worlds are chemically promising, which atmospheres are hard to explain without biology, and which environments are most likely to sustain long-term complexity. Sometimes science solves a mystery not by one dramatic answer, but by turning one huge unknown into a sequence of testable smaller ones. Gravitational wave astronomy offers another example of how mystery can shrink through new ways of observing. For centuries, the universe was read mostly through light. Now space-time itself has become a messenger. The growing catalog of gravitational wave detections has already shown that black hole mergers are not rare curiosities, but part of the actual living cosmos. The next generation of detectors, especially those in space, should widen that picture dramatically. They are expected to reveal slower, larger, and more distant systems, and to deepen our understanding of how massive black holes grow and how violent events shape galaxies over cosmic time. They may also give us cleaner tests of gravity in extreme situations, where some of our deepest questions remain most exposed. So when we ask whether cosmic mysteries will be solved, one answer is clearly yes, in part, because whole new observational windows are opening right now. There is similar hope in the study of the early universe. New telescopes continue to push observations closer to cosmic dawn, finding galaxies from astonishingly early times and giving better clues about how structure emerged from the young cosmos. That does not mean we will directly watch the Big Bang itself, and it certainly does not mean that every question about the beginning will become simple. But it does mean that the region between complete darkness and direct knowledge is shrinking. Early galaxies, background radiation, large-scale structure, and the expansion history of the universe together provide a growing archive of evidence. Some mysteries of origin may therefore become less mysterious, not because we suddenly leap to the first instant, but because the chain of evidence around it becomes tighter and more detailed. Science often advances this way. It approaches the center of a mystery indirectly, from many sides at once. And yet, it would be a mistake to let optimism become overconfidence. Some mysteries may resist final closure for reasons that are deeper than limited technology. One reason is horizon structure. If parts of the universe can never send us signals because of cosmic expansion, then questions about the total global form of reality may remain partly beyond direct empirical test. Another reason is that physics may explain how something happens without fully answering why the laws themselves take the form they do. A theory can be extraordinarily powerful and still leave open the deeper question of why that theory, rather than another one, describes reality. Science is exceptionally good at finding patterns, building predictive frameworks, and linking apparently different phenomena under common laws. It is less obvious that every meaningful human question corresponds to something that nature can answer through observation. Some questions may be too global, too foundational, or too bound up with the structure of our own concepts to admit a neat final result. There is an even subtler difficulty. Sometimes the obstacle is not missing data, but the fact that our ordinary language may stop fitting reality near the deepest frontier. Questions such as what happened before the beginning, what space-time is at the smallest scale, or whether the whole universe has a single simple global form, may assume that the world must conform to categories that come from daily life. But modern physics has already shown, again and again, that reality is under no obligation to preserve human intuition. Space and time turned out not to be separate absolutes. Gravity turned out not to be a simple pull through fixed emptiness. Matter turned out not to behave only like tiny hard particles. It is possible that some cosmic mysteries will not end with a plain answer in ordinary language, but with a revised way of asking the question itself. That still counts as progress, even if it feels less final than a simple solution. This is especially important when thinking about the dream of a final theory. Many physicists hope that a deeper framework will one day unify gravity with quantum physics and explain more of the universe in one coherent structure. That hope is reasonable. Science has repeatedly moved toward broader unification. But even a more complete theory would not automatically end all cosmic mystery. It might tell us more clearly how the universe works, while still leaving open why this lawful structure exists at all. Why there's something rather than nothing, or whether there are regions forever beyond direct contact. The history of knowledge suggests that solving one deep problem often reveals another layer beneath it. The universe explained more deeply does not necessarily become smaller or less mysterious. It often becomes stranger in a more precise way. Still, there are strong reasons not to become pessimistic. Science has often surprised people who believed the frontier had hardened into an eternal wall. There were times when the composition of stars, the existence of galaxies beyond the Milky Way, the age of the universe, and the detection of planets around other suns all seemed impossibly remote. Yet patient work turned each of these into something measurable. That pattern should make us cautious about saying that today's mysteries must remain unsolved forever. The unknown is not fixed. It shifts when observation, theory, and technology change together. Some problems truly may be limited by the structure of the universe. Others may only look that way from the current stage of knowledge. The difficulty is that we often cannot tell in advance which kind of mystery we are facing. So the most honest answer to this chapter's question is neither a confident yes nor a gloomy no. Some of the greatest cosmic mysteries will almost certainly be understood much more deeply than they are now. New observatories will sharpen the search for life, improve our picture of the early universe, reveal more through gravitational waves, and test gravity and cosmic expansion with increasing precision. At the same time, some mysteries may remain partly open because the universe has horizons, because the deepest theories are still incomplete, or because certain questions may outrun what observation can ever fully settle. Science does not promise total closure. What it promises is something both humbler and more powerful: disciplined progress, growing understanding, and a better map of what can and cannot be known. There is something beautiful in that balance. The future of cosmic mystery is not a future in which wonder disappears. It is a future in which wonder becomes more exact. The unknown does not simply retreat in embarrassment before knowledge. It changes shape. A mystery once thought magical becomes measurable, and then a deeper mystery appears behind it. That is not failure. It is the normal life of science. The universe remains generous enough to reveal much and reserved enough to keep some of its depth. And perhaps that is the right thought to end with. You do not need every cosmic mystery to be solved for the universe to feel meaningful. In some quiet way, the search itself is already one of the most extraordinary things the cosmos has produced. Matter arranged into beings who can ask where it came from, how far it extends, whether life is rare, and whether the deepest laws can ever be understood. Some answers will come. Some may remain beyond reach. But tonight, it is enough to rest inside a universe large enough to keep secrets and gentle enough in one small corner to have made curiosity possible at all. And now, my friend, as our journey through the universe comes to an end, I hope your mind feels a little quieter beneath the weightless scale of it all. If you are still awake, you might enjoy drifting into another video and letting the stars keep you company a little longer. But if sleep is finally beginning to find you, then let go of the day, let the questions fade softly into the distance, and rest beneath the silent cosmos. Sweet dreams among the stars.